Good afternoon, and welcome to the first, and maybe many, virtual Geometry Notes with Mr. Kuiper. I'm your host, Mr. Kuiper, and we are going to get after it today. So if you follow along with me, we're doing 3.3, and since your math teachers cannot be here with you to take you through this, we thought this was the next best option. So if you remember from what we did on the 60 earlier this week, we talked about a few different theorems, and those theorems were listed at the top here: the corresponding angles theorem, the alternate interior angles theorem, and the alternate exterior angles theorem. And what I want you to notice about each of these things is how it is worded, because in each of these cases, what you start with are parallel lines, right? Each theorem begins with if two parallel lines are cut by a transversal. Once again, if two parallel lines are cut by a transversal. If two parallel lines are cut by a transversal. So in each of these cases, what we are starting with is we're starting with parallel lines. And in letter A, because we have those parallel lines, we can say corresponding angles are congruent. In letter B, we say because we have parallel lines, then we can conclude that alternate interior angles are congruent. And then in C, because of the parallel lines, we can conclude that alternate exterior angles are also congruent. Okay? And the reason I point you to the wording of that is because today we're going to look at the converses of those theorems. And if you remember, the converse from last unit takes that statement and just flips the order of the if-then. So what we will see in 3.3, I will skip letter A and come back to it. But what we will see in 3.3 is that we are given the converse of the corresponding angles theorem and the converse of the alternate interior angles. So notice what happened here. We have if two lines are cut by a transversal so that corresponding angles are congruent, then the lines are parallel. So in this case, what we have is we have corresponding angles congruent first, and then we are now concluding that we have parallel lines. So this is just the direct converse of the theorem that we discussed the other day, where it was if parallel, then corresponding angles are congruent. Now we're just switching that, and we're saying if corresponding angles are congruent, then we have parallel lines. Okay, and if you want to do an abbreviation of that for your theorem table, and if you use this going forward, you can just put it like this: corresponding angles congruent, then parallel. Okay? So it's the same theorem. If you know one, you know the other one. You just switch the order of it. And that is going to be also true for the alternate interior angles converse as well. If you remember down here, or earlier, we had if parallel, then alternate interior angles are congruent. Now what we're saying is if we know that alternate interior angles are congruent, then we can conclude that lines are indeed parallel. So the abbreviation that we can use here is alternate interior angles congruent, AIA congruent, then parallel lines. It is not listed here, but the converse for the alternate exterior angle is also true. So if you have alternate exterior angles congruent, if you know, or if you are given that alternate exterior angles are congruent, then you can logically conclude that you have parallel lines. So those are the converses to the theorems that we talked about the other day. I would highly recommend putting both the original and the converses into your theorem table because we will be using both in this unit. I skipped letter A, and this is the last theorem that we are going to discuss. Actually, not discuss, because for a discussion that requires more than one person, and it's just me here. So this is the last theorem that I'm going to talk to you about today, and that is the transitive property of parallel lines. We should be familiar with transitive property. The transitive property, if you remember just in general, was if A is equal to B, if B is equal to C, then what can you conclude? you can conclude then that A is equal to C. And that transitive property we used in proofs, and we will continue to use in proofs. And the transitive property of parallel lines is very, 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 very similar. What I'm just going to do is I'm just going to replace these equal signs with parallel lines. So what we have here is if two lines are parallel to a third line, then they are parallel to each other. So if A is parallel to B and B is parallel to C, then we must know that A and C are also parallel. Okay, so remember these straight up and down lines here are notation for parallel. I'm not putting the number 11. So that is notation for parallel. So we have if A is parallel to B and B is parallel to C, you know that, then you can conclude that A is parallel to C. Okay, it says write these properties using L, M, and N, but if you use A, B, and C, that's fine. So if you know that A and B are parallel, if you also then know that B and C are parallel, then you also can conclude that A and C are parallel. So this is the final proof that we're going to discuss, or the final theorem, excuse me, that we're going to talk about for today. So really there's just a few new ideas, the first of which being the converse to the theorems that we talked about on the 6D, which are written here. Just flipping the if-then statement from what we did in 3.2. And then the transitivity of parallel lines. Okay, so what we're going to do is we're going to practice this a little bit. There are two more proofs in this section in your notes. We're going to do those together. And follow along with me. What we're doing first is we are proving the alternate interior angles theorem. And remember what the alternate interior angles theorem just says. The alternate interior angle just says if you have parallel lines, then you know that alternate interior angles are congruent. So that is why we're trying to prove that angle 1 is congruent to angle 3. Because if you notice angle 1 and angle 3, these things are indeed alternate interior angles. So if we can start with the fact that we have parallel lines and can show that angle 1 is congruent to angle 3, then we have proven the alternate interior angles theorem. Now, we know the alternate interior angles theorem is true, so technically this could just be a one-step proof. You write your given and then you say 1 is congruent to angle 3 because of alternate interior angles, but that's what we're going to try to prove. So we can't use that theorem if we're trying to prove it to be true. So we're going to try to do this in another way. So as in any proof, the first thing that you start with is your given. What are we given? We're given that line O is parallel to line N. We did not earn this information. That information has been given to us. We are recipients of this wonderful bit of news that O and N are parallel. Okay. Because they're parallel, we can't use the alternate interior angles theorem because that's what we're trying to prove. But since we're given parallel lines, immediately what we should think to is all of the theorems that we've been discussing that have been dealing with parallel lines. So we're doing the alternate interior angles theorem. That's what we're trying to prove. A couple other ones were alternate exterior angles and corresponding angles. So if you're given parallel lines, what the next logical thought would be, okay, because I have parallel lines, what type of angles are congruent? And if you notice, because these things are parallel, we can conclude that angle 1 is congruent to angle 2. And the reason that angle 1 is congruent to angle 2 is because they're in the same position. Notice they're kind of, if you cut this piece in half, they're both in the top left region. And the theorem for that is corresponding angles. So our reasoning is if parallel, then corresponding angles are congruent. So we say if parallel, which we have, then corresponding angles are congruent. So I know that angle 1 and angle 2 have to be congruent. And I can even come over here and mark that so we can see that as well. Ultimately, we're trying to prove that angle 1 is congruent to angle 3. So somehow angle 3 has to get in the picture here. And this is now where angle 3 gets in the picture, because now we're going to say that angle 2 is congruent to angle 3 as well. And this is a very, very, very common theorem that hopefully you know by now. And when they're straight across from each other like this, those are vertical angles. So we say if vertical angles, then congruent. That is why 2 and 3 have to be the same. And lastly, hopefully you can see now, we can say that angle 1 is congruent to angle 3. Because if 1 is 2, 2 is 3, so you have 3 pieces of information here. 1 is 1, 2, and 3. And hopefully I clued you in from the theorem that we talked about earlier. If 1 is 2 and 2 is 3, why can we conclude that 1 is 3? That is the transitive property of equality. So now we've just shown that angle 1 is congruent to angle 3. So we have proved that if you have parallel lines, then it must be true that alternate interior angles are indeed congruent. Are there any questions? Okay, that was awkward. Let's do the last one and then I'll be done. So in this one, we're trying to prove the consecutive interior angles theorem, or just looking here, if we're given that O is parallel to N, what we're trying to prove is that 1 and 3 are supplementary. So once again, we start with our given. We say that O is parallel to N, and that is our given. And I gave you kind of this clue last time. As we think through proofs this unit, you're given parallel lines. So you go to your toolbox and you're like, hey, I'm given parallel lines. What does that tell me? Well, that tells you that you have corresponding angles congruent. And that tells you you have alternate interior angles congruent. That tells you you have alternate exterior angles are congruent. So odds are you're going to probably use one of those things. And in this case, again, we're going to use the fact that corresponding angles are congruent. So we will conclude here that angle 1 is congruent to angle 2. Because once again, if you notice, those are in the same position. So then the reasoning is if parallel, then corresponding angles are congruent. Because in the numbered angles here, why did I choose corresponding angles and not the other ones? Well, do I have any alternate exterior angles labeled? Well, this one would have needed to be labeled to use alternate exterior angles, so I'm not using that one. And I don't have any alternate interior angles labeled as well either. So the only pair of angles that I have here that are labeled with a number or corresponding angles. So that can also kind of clue you in as to what theorem to use, or why I chose corresponding angles instead of another one. Okay. Ultimately, what we're trying to prove here, though, is that angle 1 and angle 3 are supplementary. So at this point, you're kind of like, I've shown that 1 is congruent to 2. Where do I go from here? Well, this should clue you in. You're trying to prove that things are supplementary. So you should start throwing some supplementary in here. And what you know right now is that angle 2 and angle 3 are supplementary. The reason you know that angle 2 and angle 3 are supplementary is because they're linear pairs. And so we have a theorem that said if you have a linear pair, then you have sup angles. Sup angles. Or supplementary for you, those that are less lazy than I am. So LP, I'm just abbreviating for linear pair. So if you have a linear pair, then you have supplementary angles. And if you look at 2 and 3, those certainly are a linear pair. And now because you have supplementary angles, what's the only thing we know about supplementary angles? Well, the only thing that we know about supplementary angles is that their measures, when you add them, has to equal 180 degrees. So yeah, angle 2 and 3 are supplementary. What does that mean? Well, what that means is that when you take those two angles and add them together, you're going to get 180. Okay? So then how we abbreviate, or how we give reasoning for that is if we have supplementary angles, then the angle sum is 180. So let's take a little step back here and see what we've done. So we've shown that 1 and 2 are the same. And then we said, okay, well, 2 and 3, they're supplementary, which means that they add up to 180. Ultimately, what we're trying to show is that angle 1 and angle 3 are supplementary. Okay? So at this point here, what I would highly recommend doing is recognizing that angle 2 plus angle 3 is equal to 180. What you can do then is, because 1 and 2 are the same, you can swap one in for the other. So now we can say that the measure of angle 1 plus the measure of angle 3 is equal to 180. And when you swap something in for something that is equivalent, that is called substitution. Property of equality. And then now, if you look at our most recent line, what we have is that the measure of angle 1 plus the measure of angle 3 is equal to 180. So then because 1 and 3 add up to 180, you can say that angle 1 and angle 3 are indeed supplementary. Okay, so then the reasoning for that is, now if the sum is equal to 180, which is what we have, then supplementary. Right. So it's a little nitpicky here because you have to start with linear pairs to get supplementary, and then you show that they add to 180, and then do substitution, and then conclude that angle 1 and angle 3 are supplementary. If you would have jumped up to here, and from this step right here, just easy for me to say. At this step right here, if you would have done substitution and said angle 1 and angle 3 are supplementary by substitution, I think I would have accepted it. But this is the probably by the book the way you're supposed to do it. So that's why I wanted to show you it in that way. Okay? So thank you for tuning in. Hopefully it wasn't too awkward. And for the remainder of the time in this period, what I would highly recommend doing is completing your one-step proof worksheet that you will receive. Also, if you finish that, you can correct it on Moodle. And upon correcting it on Moodle, I would also then use your time updating your theorem tables. So we've talked about a lot of theorems over the last few days, and you'll want to make sure that those are updated, because we will have a quiz over this 3.1 to 3.3 material on the 60 next week before your break. So please make sure you're ready for that, and you can use your theorem tables for that, so that will be a helpful resource for you. Thank you for tuning in. This has been Geometry with Mr. Kuiper. I hope you enjoy. Have a wonderful, wonderful rest of your day.